All right, hi guys. Here's the first part of the slides from chapter 9, which is going to be about energy. Um, yeah, here we go. So earlier in the year, we talked about adding two vectors together. We talked about a couple of different ways to do that. What we're looking at here in this picture, this looks like the parallelogram rule. A rectangle is a parallelogram. We also talked about the tip to tail. So we've discussed adding vectors. We've also done step 0, which is the opposite of adding vectors. It's taking one vector and breaking it up into two vectors. So that's how addition works with vectors. So the question now for chapter 9 is, what does it mean to multiply vectors? If you multiply a vector by a vector, what do you expect the product is going to be? Are you going to get another vector, or are you going to get a scalar, or are you going to get something else entirely? And the correct answer is, there's actually two correct answers. One way to multiply vectors is called the dot product, also called the scalar product, where you take a vector, dot it to another vector, and you end up with a scalar. So notice the hats. A and B were vectors. A dot B gives you C. C is a scalar. So here's a formula for that. And the other way of doing this is what's called the cross product, also called the vector product, because A cross B gives you C, which in this case is also a vector. In this chapter, we're going to be dealing with this top one, the dot product, aka the scalar product. So this chapter is chapter 9, energy, work, and power. So what is work? When you have a force acting through a displacement, remember that displacement is the vector version of distance, that produces work. So the way you would read this sentence mathematically is you would say F dot D equals work, or force dot displacement equals work. There is a vector way to do this math. We're not going to have to do that. If you take physics in college, you'll learn how to do it the vector way. We're just going to do it this way. So these absolute value signs here, what they really mean is magnitude. So you could say the magnitude of force times the magnitude of displacement times cosine of theta, the angle between them, gives you work. And if you're feeling lazy, you would not even say the magnitude part. You would just say FD cosine theta. And the magnitude part is just implied. So the three things you need to know if you're going to calculate work are, what is the magnitude of the force? What is the magnitude of the displacement? So just the positive numbers of these guys, ignoring their directions, and the cosine of the angle between them. That will give you work. So work is a scalar quantity. The unit for work is joules. So here's James Prescott Joule, after whom the unit of work is named. What did he do? I think he found the connection between mechanical work and heat, I think is what he did. And to honor him for that, we named the unit of work, and you'll find out too, also the unit of energy after him. So here's this slide. Your quantity is work. Its symbol is a capital W. Its unit is the joule, which you write as a capital J, and work is a scalar. Notice work is hatless. That makes it a scalar. So this situation, one, I'm a little annoyed that these don't line up. These arrows all fit nicely in these boxes when I'm casting it on the Samsung TV in the classroom. But apparently I've got a different aspect ratio or something on my MacBook, so it's not lining up. I'll get over it. So anyhow, 4 important cases to think about. In all 4 cases, this object is going to be displaced to the right. So the red arrow going to the right in all 4 cases represents the displacement. The blue arrow represents the force. So let's look at these case by case and try to figure out what's going on. So in the first case, the thing was displaced to the right, and the force that we're interested in is also acting to the right. So the question is, what is the angle between these two vectors? So hopefully you can see pretty quickly that the angle between these guys is 0 degrees. There is no angle. There is an angle. It's 0 degrees. Ask your calculator, what is the cosine of 0? The cosine of 0 is going to give you 1, which means what kind of work is going to be done here? Well, we've got the magnitude of the force. The magnitude has to be positive, times the magnitude of the displacement, which is also going to be positive, times cosine of 0. Cosine of 0 is 1. So positive times 1 is going to give you positive work being done in this case. Now, the next case, Again, the thing is displaced to the right, but the force we're interested in was acting to the left. So the angle between the displacement and the force is 180 degrees. So theta is 180 degrees. What is the cosine of 180 degrees? Either memorize it or ask your calculator. The cosine of 180 degrees is -1. So what kind of work is done in this case? Well, positive times -1 is going to give you negative. So this will do negative work. Third case, displacement to the right. The force we're interested in is acting up. So what's the angle between our displacement and our force? It's 90 degrees. This is a right angle. So theta is 90. Cosine of 90 degrees is 0, which means when we figure out what kind of work is this force doing, you're going to have a positive times 0. Your answer is 0. There's no work being done in this case. So just to be clear, some people don't like this idea. They struggle with it. Your force is not 0. Your displacement is not 0. But the angle between them is 90. Cosine of 90 is 0. So this force is not going to do any work. The same thing would also be true if you had a force going down. In this case, that would also be, you would call that angle -90. And the final case, I wish that would stop popping up, that little thing there. You've got displacement to the right, and the angle you have is just an arbitrary angle. It's not one of these nice ones. It's not 0, it's not 180, it's not 90 or -90, it's just some angle. In that case, theta is going to be some arbitrary number. Cosine of theta is going to be positive or negative. And the work done, it's going to depend. So here are your answers for that. So if you remember when we actually did this in class, I pushed a book to the right across the table. My question was, what forces are acting on the book, and which of those forces do positive, negative, or 0 work? So if I push the book to the right, there's a force of me pushing on it. So I'm calling that F sub A for force applied. There's also friction. So if I push this thing to the right, friction opposed the motion, so friction went to the left. There was a normal force. The book was touching the table, which means the table was pushing on the book. So there was a normal force going up. And there's also gravity because we're doing this on Earth, and all of the mass of the Earth is pulling the book straight down. So if we draw a free body diagram, it would look like this. And again, I push this to the right. So imagine another displacement vector going this way, also to the right. So which of those forces do positive, negative, or 0 work? So we'll start with force applied. That's a positive number. Well, the magnitude is always going to be positive. The absolute value signs mean use the positive number. The displacement is also going to be positive. The magnitude of the displacement is also going to be positive. Times cosine of theta. So if this thing goes to the right, what's the angle between this force and the displacement? It's 0 degrees. Cosine of 0 is 1. So force applied would do positive work. If we looked at the normal force, so positive times cosine of the angle between displacement going to the right and this is going to be 90 degrees. Cosine of 90 is 0. So the normal force does no work. Now we'll look at F sub K, the force of kinetic friction. Positive times cosine of this angle. We went this way. This force is going the other way. The angle is 180. So cosine of 180 is -1. Friction does negative work. Turns out friction will always do negative work. Friction will only ever take energy out of your system. It won't put energy into your system. And the last force we're looking at is the force due to gravity. So displacement to the right, force of gravity going down. That means there would be a right angle in here. So that displacement, cosine of a right angle, cosine of -90 degrees, is going to be 0. So the force of gravity does no work. So here are your answers to that one. You can compare these to the previous slide. These guys right here. So the cases we dealt with here were this, and the upside down version of this, where the force is to the right. The displacement is to the right, but the force was going down. So quick review. What is the symbol for work? I'm going to give you a little pause. If you're watching this at home, Actually think about these and come up with your answers. So what is the symbol for work? That's not too bad. Capital W. Sometimes their symbols make sense. Next question. What are the units of work? Well, look at this guy over here. Maybe that'll help you remember. The units of work are joules. Capital J for joules. Here's James Prescott Joule. Is work a scalar or a vector? Try to remember, does work wear a hat or not? If it wears a hat, it's a vector. If it doesn't, it's a scalar. Work does not wear a hat. Work is a scalar. And what is the formula for work that we learned? The formula for work is work W equals magnitude of force times magnitude of displacement times cosine of theta, which is the angle between those two vectors. And that's the end of the slides for today. So hopefully that helped.